Okay, so in this video, we'll talk about the second half of chapter 44, which is the topic of cosmology. Okay, it's a really fun topic. Cosmology is a branch of astronomy and astrophysics that studies the universe as a whole. So it's studying large-scale structures in the universe. It's basically studying everything, the origin, the evolution, the future of the universe. Interestingly, cosmology, which is the study of the huge universe as a whole, has a close relationship with particle physics, what we talked about in the first half of this chapter. Um, there's a lot of evidence, which I'll talk about in these slides, that in the early part of our universe, there were no galaxies, there were no stars, there were no atoms, there were only particles. So, how particles behave, how they interact with each other, what particles exist, um, that information has a big impact on the actual predictions of cosmology. Um, of course, cosmology also has a close relationship with observational astronomy. So experimental cosmologists often work on telescope experiments, for example, or in other cases, space telescopes, and we'll talk more about that also in a few slides. In the last 2 decades, there's really been a revolution in cosmology, just in terms of the number of dedicated experiments, dedicated to studying the universe as a whole, cosmological structures, the cosmic microwave background, etc. And so it's a really great time to get into cosmology right now. There's a lot of really cool experiments coming up in the next few years also. Okay, so just as we did with particle physics, we'll go through the cosmology a little bit historically. So I'll start in 1912. This person, Vesto Slipher, and you can see Vesto's picture in this cool picture from 1905 from the 24-inch telescope in Flagstaff. So Vesto, who's actually from Indiana, worked at Lowell Observatory in Flagstaff, and Vesto was the first person to use a spectrometer to observe the spectra of galaxies. So this happened in 1912, and using a spectra, he could measure things like the fact that spiral galaxies are actually rotating, and he was also able to discover that galactic redshifts, meaning that he could observe the spectra of a galaxy and see that the spectral lines are shifted, indicating that they're redshift, that galaxies are in some cases moving away from us. At the time, they didn't really know about galaxies; they just called everything nebulae. But he was able to note that most of these galaxies are actually moving away from the Earth. Right, their spectrum is shifted; the spectral lines were all shifted. Okay, moving on to history. In 1922, a Russian scientist named Alexander Friedmann derived what are known as the Friedmann equations based on Einstein's general relativity. And with these equations, it became clear that it was possible the universe could be expanding, which is, of course, a very different idea than what was kind of the current model at the time and the model accepted by Einstein, which was the static model, that the universe was infinite in size and not expanding or contracting. So the Friedmann equations at least showed it could be possible that the universe was expanding. In 1924, Edwin Hubble did some further research and discovered that these spiral nebulae, these objects that everybody was observing, were actually galaxies outside of our galaxy, so it took a little while for everybody to realize that fact. In 1927, Lemaitre from Belgium proposed that the fact that a lot of galaxies were moving away from us was due to the expansion of the universe. So we'll talk more about that in a couple slides. And then in 1929, Hubble again, he developed a series of methods to measure the distance to astronomical objects. So this is a forerunner of the cosmic distance ladder. This is how astronomers are able to measure how far away different objects are, and there's a series of ways they do that. For things that are closer, they use one method. For things that are an intermediate distance away, they use a different method. And this is a cosmic distance ladder. It's how you can have a good measurement of how far something away is. So Hubble developed some methods to measure distances, and with that method, he discovered that there's a correlation between the distance to a galaxy and its recession velocity. So not only are galaxies typically moving away from us, but those that are farther away from us are moving faster away from us. And so this is called Hubble's law. So talking a little bit more about Hubble's law, um, again using Doppler shift to measure the velocity of galaxies at some distance away from us. And on this graph here, you can see on the x-axis is the distance away from us. That's measured in megaparsecs. And on the bottom left here, there's a couple things just to give you some picture into what is a megaparsec. So the Andromeda galaxy is about 0.78 megaparsecs away from Earth. So that's 2.5 million light years. And the nearest large galaxy cluster, the Virgo cluster, is about 16.5 megaparsecs away from the Earth, which is 54 million light years. So that gives you a little bit of a picture of how big a megaparsec is. So the x-axis is distance, the y-axis is the velocity. How fast are these galaxies moving away from us? And you can see there's a nice linear relationship where the farther away a galaxy is, the faster it is moving away from us. Okay, so this is called Hubble's law, and the slope of this linear fit here is called h sub 0, or Hubble's constant. And so this is something that is a really important thing to study, has a profound effect on just understanding our universe as a whole. Your textbook has the Hubble constant as being 67.3 kilometers per second per megaparsec. Okay. If you look at a lot of recent measurements, you can see there's a little bit of a variation in these measurements. And this is the kind of beautiful kind of scientific result you want to see, where a lot of different experiments have different measurements. Each one has different accuracy. All these experiments have error bars, which are an approximation of the uncertainty on their measurement. You can see throughout all these measurements there is a spread, and putting all these measurements together, you could have a pretty good estimate of the current Hubble constant. So, okay, a little bit more about the expanding universe. So this is something that you could predict with general relativity, and that the redshift of galaxies could be due to the expansion of space itself. So why is it that all galaxies we see are moving away from us, and those that are further away are moving even faster away from us? Well, people often use this analogy of a balloon, where you could draw two spots on the balloon, and there's some distance between those two spots. Right? And then as the universe expands, the balloon gets bigger, and not only do these 2 points get further apart, but the rate of change of distance between 2 points is proportional to their distance apart. So the further away something is, right, it appears to move faster away from us. So that's kind of a nice model of in your head how you can think about the expanding universe. Okay, continuing on with our history a little bit. In 1931, Lemaitre suggested that the universe is expanding, and that this means that in the past it must have been smaller. And if you project that back in time, even further, it was even smaller. And you keep projecting it even further back, the universe was really small, and you get to a single point, which Lemaitre called the primeval atom. And that was the point where the universe came into existence. So that was the first suggestion of kind of the Big Bang idea, which I'll talk about in a moment. This idea was not accepted at first. The static universe concept was still accepted. In 1947, in the face of all this evidence that all these galaxies are moving away from us, new models were suggested. These were called SteadyState Models by folks like Bondi, Gold, and Hoyle. They suggested the universe is expanding, but it doesn't look different as time goes on. So how can that be? The universe is expanding, but it doesn't look different as time goes on. And what they suggested was that even though the universe is expanding, its density remains constant. And how does that happen? Well, matter would have to be continuously created. Right? If the universe is expanding, if the volume is increasing but density is staying constant, the mass must be also increasing somehow. So they suggested that matter was somehow being created in the universe. Okay, so steady-state models were, something commonly discussed around 1947. In 1948, Gamow demonstrated that using Lemaitre's expanding universe theory to think about the hot, dense early universe, one could actually use that fact that the early universe was hot and dense to predict the relative abundances of elements in the universe. Okay, so the fact that there's some percentage of hydrogen and some percentage of helium and things like that in the early universe, you can actually predict that by modeling that early part of the universe. And this later became known as Big Bang nucleosynthesis. But the fact that this model could make predictions about the relative abundances of elements gives it some credence, right? And okay, let's just talk a little bit about nucleosynthesis for a second here. Um, and okay, so after the Big Bang, the universe was composed of 75% hydrogen and 25% helium. Um, and in general, the heavier elements, up to iron, were formed later in nuclear reactions, right? In fusion in stars, and also when stars are blowing up, they also can create some of these elements. So that's an exoergic reaction, right? In fusion, where energy is released, acid is also creating these larger elements. Elements heavier than iron can only be formed in endoergic reactions, right? You need to put energy in. And so this happens in supernova and the explosions of heavy stars. And these elements get, thrown out all in space and see the next generation of stars. So things like our sun were formed out of a gas cloud that already had some of these heavy elements in it. And that's how, of course, Earth formed and things like that. And of course, anytime you see a nice nebula like this, the Veil Nebula, this is a remnant of a supernova explosion that occurred more than 20,000 years ago. So just, yeah, beautiful picture. Okay, but anyway, going back to the history, in 1948, Alpher and Herman used Lemaitre's expanding universe theory to think more about the hot, dense early universe, and they predicted something called the cosmic microwave background, that in the early universe, if you had all these particles floating around, and if it was really a hot, dense soup of particles, then light couldn't travel very far. Anytime you produced a photon, it would be quickly absorbed in this hot plasma. But as the universe expanded and cooled, once atoms formed, light could then escape. It could then travel some distance, and that light, corresponding to whatever temperature the this hot, dense universe had at that moment, would still be traveling through the universe, and you could maybe be able to detect it. Okay, and now it would be microwaves, because as the universe expanded, the wavelengths would have changed. So this was predicted in 1948. In 1949, Fred Hoyle, who was one of the supporters of the steady state theory, coined the term the Big Bang in order to contrast his preferred steady state model to Lemaitre's model. Okay. In 1950s, there were a lot more studies of distant radio sources in the universe, objects emitting radio waves, and these measurements gave some more evidence in support of the Big Bang model. And in 1964, right, almost 20 years after the cosmic microwave background was predicted, the cosmic microwave background was discovered. This is a really interesting story also. These two folks, Wilson and Penzias, accidentally discovered the CMB in New Jersey using a radio device that they thought they were hearing electronic noise. They thought there was a problem with their detector, but what they were actually observing was this microwave background. And also, interestingly, another team had just started looking specifically for the cosmic microwave background. So the two folks who weren't looking for it found it before the people who were specifically looking for it. But with the discovery of the cosmic microwave background, this really led everybody to now decide, okay, this Big Bang model, Lemaitre's model that the early universe was hot and dense and has been expanding since then, now becomes accepted. Okay, a little bit more about this background radiation. So about 300,000 years after the Big Bang, the temperature of the universe was about 3,000 Kelvin. It was at this time the universe suddenly became transparent. Okay, all those particles that were flying around finally were able to form into atoms. Okay, and now photons could travel some distance. So this radiation, this 3,000 Kelvin blackbody radiation, survived and kept flying through the universe. And as the universe has expanded, it has cooled to now be about a 2.725 Kelvin temperature. And this is, again, some of the best evidence we have of the Big Bang theory. Okay, and this is a really nice image measuring the cosmic microwave background, and I'll talk more about that in the next couple of slides. So, a little out of order here, sorry. Okay, let me talk a little bit more about the CMB real quick. The cosmic microwave background, again, this is the relic electromagnetic radiation filling all of space. It's about 2.3 Kelvin, and so if you measure, the radio waves floating through space, you get data that looks like this. So there's a range of frequencies, and this is from a whole bunch of satellites. COBE is one of them, Planck is another. There's all these amazing satellites that have been able to measure the cosmic microwave background in great detail. And what you see in images like this is looking at the entire sky. So this is the cosmic microwave background from one area of the sky, and this is from a different area of the sky, etc. You see all these variations in the temperature. Okay, now this may look like a lot of variation because there's red and there's blue and etc. But the variations are actually tiny. So on the whole, the spectrum is all about corresponding to a black body with about 2.3 Kelvin of temperature. And you can see in the green line here, this is the predicted black body spectrum, which really closely matches the data. So in general, the spectrum matches that of a 2.3 Kelvin black body radiator, but there are tiny variations in it throughout the sky, about the 18 microkelvin level. So on the whole, the black body radiation is extremely uniform, isotropic to 1 part in 100,000. But there are these very small variations, which actually have a ton of information in them, and current scientists, like those working on the Planck telescope, are studying these variations. Okay, and then again, continuing with our history, in 1970, Penrose and Hawking come up with some nice physics describing the singularities, such as those in the Big Bang. And then in 1981, Guth introduced the concept of inflation. This is the idea that the rate of expansion of the universe is not constant, that there was a time period shortly after the Big Bang where the universe expanded very rapidly. So the universe is expanding now, but in the beginning of the universe, it is expanding much, much more rapidly. And in Guth's model, this inflationary model, this inflation leads to this homogeneous isotropic flat universe that we observe today. Right? So if you look out in the universe, the density of stars and galaxies in any particular direction is pretty much the same. If you look at the CMB, as we talked about, it's really uniform everywhere in the sky. And how can that be? It was this inflation. It turns out that inflation predicts this homogeneous universe. Okay. The question is, what was driving this inflation? What caused the universe to expand so rapidly? Okay. And people are still trying to research that, and there's all sorts of models. And this is really an area where there is active study going on right now, both theoretical and experimental research going into this question. But it could be there's some kind of a field that we haven't discovered yet. With the discovery of the Higgs boson in 2012, we discovered, for example, there's a Higgs field in the universe, and a Higgs boson is propagating in this field. It could be there's another type of field which causes the universe to expand so rapidly. So that's an area of current research. Okay, so putting it all together, we have, I think I have 4 different of these nice pictures of the history of the universe, and they all have their merits, so that we can go through them one by one. So in our kind of complete picture of the universe is about 13.7 billion years old, or at least it's been about 13.7 billion years since what we're going to call the Big Bang, and I'll talk more about that in a couple slides. But we have this idea of the Big Bang, we have a universe, and kind of the separation between these two lines is kind of a rough approximation of the size of the universe. So the universe is kind of expanding, and about 10 to the minus 36 seconds after the Big Bang, where the universe as a whole is extremely hot and dense, energy about 10 to the 16 billion electron volts, we have this period of really rapid expansion of the universe. Okay, so that's the inflationary period. then about 10 to the minus 10 seconds after the Big Bang, we have this universe where there are only particles. There's quarks and gluons and electrons and W bosons and perhaps dark matter floating around in the universe. And by about 10 to the minus 4 seconds, you start to form nucleons. So some of the quarks can kind of come together and form a proton, for example, or a neutron. And so you start getting, strong force holding quarks together to form bound states. About 10 to the 2 seconds or so, you start to get nucleons, so protons and neutrons start to come together. So we still have this really hot, dense universe, which is very uniform everywhere. Everywhere you look, there is just a hot, dense plasma of protons and neutrons and electrons and things like that. And some of those protons and neutrons start to come together and form bound states through the nuclear force. And a good period of time later, so this is again 10 to the 2 seconds after the Big Bang. Here we're at 3 times 10 to the fifth, so this is 300,000 years after the Big Bang. This is when the universe, as the universe is expanding, it's cooling, and this is about the time when these nucleons can start to grab some of those electrons and where you can start to form atoms. Right? And once you get atoms forming bound states, photons can now travel. And so this is the period where the cosmic microwave background radiation is released, basically. As the universe continues to expand and cool, all the hot gas, all these hydrogen and helium produced during this period starts to form stars and galaxies, etc., structure in the universe, and the universe is continuing to expand and cool, and today we see, stars and galaxies in the universe, right, about 13.7 billion years after this Big Bang. Interestingly, evidence now suggests that the expansion rate of the universe is actually increasing, and so we don't really know why. There's this concept of dark energy causing the universe to expand, and the rate of its expansion seems to be increasing. But this is again something that's actively being studied. So we can go back and, with our experiments, try to study the history of our universe. Right? We can look at a galaxy which is 13 billion light years away from us, and the light has taken 13 billion years to get to us. So we can study what the universe was like 13 billion years ago, for example. We can also look at the cosmic microwave background, which is radiation, which has been traveling through the universe for 13 billion years, more than 13 billion years. And we can't really see anything further back than the cosmic microwave background because, again, light wasn't really traveling. But we can, in things like nuclear collisions, like those that happen at the RHIC accelerator at Brookhaven National Lab, or at the Large Hadron Collider, which also collides heavy ions, you can start to create things like this quark-gluon plasma in the early part of the universe. And at the LHC, we can study the particles in the early part of the universe. So we can still study a lot of the history of the universe here on Earth. Okay, and there's a few other nice pictures I'll just click through here. Here's another nice history of the universe that again demonstrates the inflationary period, the period with all the particles, the period where we start to get nucleons forming, the period where we start to form atoms. This is the recombination. This is when the cosmic microwave background becomes visible, and then the star formation, etc. Okay, this is another nice picture which has some interesting pictures hidden in it, and here's another nice picture. So you can go in on your own and look at these in general. Okay, and actually a lot of particle physics comes into play here. Obviously in this period of the universe, we have all these particles interacting with each other, and our current model of the particles helps us to understand the formation of the universe. In fact, looking at the behavior of the particles, what we've observed is that at very high energies, two of the forces, the electromagnetic force and the weak force, right, seemingly two very different forces. The electromagnetic force, is responsible for pulling electrons towards the nucleus of an atom, where the weak force is responsible for things like beta decay, turning proton into a neutron and things like that. Um, these seemingly very different forces actually originate from one force, the electroweak force, at very high energy. So these forces unify. Okay, and so in the early part of the universe, there's a thought that maybe all the forces were one force, and as the universe cooled and expanded, the forces actually split into being different forces. Now this is something still being actively studied, but it's an interesting thing to think about. Okay, I wanted to talk a little bit more about the Big Bang. The Big Bang, you have to be careful with semantics here. The phrase the Big Bang means very different things to different people, so if you're talking about it, always define what you mean. Right? In some cases, the Big Bang is just this cosmological model. It's a model of the creation of the universe. In some cases, the Big Bang is not the creation of the universe, but instead just kind of starting with the fact that, okay, 13.7 billion years ago, there was a hot, dense state of particles which expanded, and this is a model that takes us from that hot, dense state to now, right? And doesn't talk anything about the creation of the universe at all. And in other cases, the Big Bang may refer to just the inflationary period, right? That was a Big Bang, that was the universe rapidly expanding. Where in other cases, the Big Bang could be the concept of a singularity, where if you really extrapolate back all the way, if the universe, is expanding, then extrapolating back all the way, the universe must have originated from some tiny piece of space which has expanded to the entire universe. So that's the concept of a singularity. So in some cases, the Big Bang refers to that. So you have to be a little bit careful when you're talking about the Big Bang. What are you actually describing? I like to talk just about the evidence, right? The cosmic microwave background and other astronomical observations provide extremely strong evidence of the expansion of the universe from a hot, dense state. This concept of recombination, that atoms first form, when atoms become neutral, right? The protons and the neutrons combine with the electrons to make this neutral object. That allows photons to travel long distances. This is the concept of photon decoupling. Photons can now travel long distances, and that's the cosmic microwave background. Um, there were no stars or galaxies 13.6 billion years ago, right? We can even directly observe light, which has been traveling through the universe for billions of years. So we have all this evidence for this model of the hot, dense state of the universe expanding to create our current universe. Before recombination, right? Before the cosmic microwave background was um, emitted, we actually do know more, right? Even though we can't directly see any light coming from, that period of the universe, we can study it in other ways. Nucleosynthesis gives us really strong evidence for the predictions of the Big Bang model during this time period, right? So if you just predict what happens if you have this hot, dense soup of all the particles we know about and all the forces we know about, and plug into that, the expansion of the universe, what you get out is a prediction for the percentage of hydrogen and percentage of helium that we have in our universe. So nucleosynthesis is an amazing evidence for this model. Um, the cosmic microwave background also gives indirect evidence for inflation, right? The fact that it's so uniform is an indirect evidence for this inflationary period. And we can also, as I mentioned, recreate some of these conditions using particle accelerators. What about the actual Big Bang, this concept of the beginning of time and space? Um, the way I like to think about it is that singularity is an extrapolation. Um, Really, this is evidence that our models are breaking down, right? We need new models. We don't have a model that combines general relativity and quantum mechanics, for example. So a new model, something like quantum gravity, could help us explain the better universe better. Um, so I think really anytime you have a singularity in physics, it often means your models are breaking down. And just so you know, there are plenty of models which are currently being discussed by cosmologists, which are really, thought of well, which include inflation, which are alternatives to the idea that the Big Bang was the beginning of time and space. For example, there's the Big Bounce model, where there was a universe before, and the universe kind of collapsed and then expanded again. And that's we've only been measuring it since it's been expanding again. So just to let you know, there's a lot of different models, and this is It's a really fun time to be a cosmologist because there's really a lot of active discussion going on in this world. And just here's a nice table from Wikipedia. If you remember our redshift that we learned about in relativity, this is a list of the most distant astronomical objects that we've measured the redshift of. So we've got a galaxy at a redshift of 11, which corresponds to 13.39 billion light years away. So that light from that galaxy has traveled for 13.39 billion years. So that's just absolutely amazing that we can see galaxies where the light has been traveling for that long. Just a quick mention of all of the cool research going on in the world of cosmology right now. We've got things like the Planck telescope, which is this really accurate, amazing space telescope. And so that's a really active collaboration with a lot of people analyzing the data from it. We've also got experiments on Earth measuring the cosmic microwave background. Like this is the South Pole telescope at the South Pole in Antarctica. So that's can study the cosmic microwave background with great detail and benefits from the kind of high, dry air at the South Pole. And interestingly, I had a friend who wintered at the South Pole. He stayed the whole winter there, and his job was to go and brush snow off of the telescope. So pretty amazing that some people get to do that. There's also telescopes on Earth that are looking at visible light instead of microwaves. For example, this was actually recently renamed, but previously it was called the Large Synoptic Survey Telescope. It's been renamed the Vera Rubin Telescope after one of the great astronomers of the previous century, Vera Rubin. And so this telescope is currently being constructed in Chile, and it's pretty amazing. It's about 8.4 meters diameter mirror. It's going to take pictures every 15 seconds. I'm sorry, it's going to take 15-second exposures, etc. Excuse me. It's basically going to be able to take movies of the entire sky every night. And with that, you're going to be able to study the motion of the universe as a whole. It's going to be able to study gravitational lensing, which I'll talk about, supernova, measure a lot of spectra. So it's a really neat experiment, and one that is, currently being constructed, something that you could go in graduate school and work on. It's a really neat project. The Sloan Digital Sky Survey was another really neat project, which was studying, which was using a whole bunch of telescopes all over the world to study, to measure the spectra of many different objects and measure the expansion of the universe. And of course, in the last few years, we have a new way of studying the universe, which is gravitational waves, which is a whole new way to study, not with photons, but now with gravitational waves, study the universe. Here's a quick picture of the mirror being constructed for the Vera Rubin telescope. So really cool. Tony Tyson was a former professor of mine. He's right there in that picture. So, okay, lots of cool stuff going on. Just a few other things to note. There's something called the Sloan Great Wall. You can actually measure great distances and study the kind of relative density of objects in the universe. And so this is this picture is kind of encompassing a huge area. This is looking, each of these clusters of dark spots here of not a star or a galaxy. These are clusters of hundreds of galaxies. And you can see that the clusters of galaxies, you get these kind of string-like structures where gravity has kind of brought everything together in these interesting formations over huge distances in the universe. And actually, there's some areas where the density is much higher than others. For example, the Sloan Great Wall. So this is something people are currently studying, as these huge structures at huge distances in the universe. We can try to understand some of the relative distances in the universe using this nice image. So this is a approximate diameter of the sphere in light years on a log scale. So we have planetary system, We have star clusters, right? Kind of our local cluster of stars. A galaxy, is about this size here. Again, on the log scale. Then we have a group of galaxies. Then we have a cluster of galaxies. Then we have a supercluster of galaxies. And then on huge, huge scales, we have these walls and voids in the universe. And then um, finally, we have the observable universe, meaning if the universe is only 13.7 billion years old, we can only see light from things that are at most 13 billion light years away. Other things about cosmology. You've probably heard about this before, but what our current understanding of the universe tells us is that only 4.9% of the matter in the universe is actually conventional matter, meaning things made out of quarks and gluons and protons and neutrons and hydrogen and helium and just all the matter we know about. Right? Only 4.9% of the universe seems to be made out of that type of material. We also have about a quarter of the universe being dark matter, some type of material that interacts gravitationally and affects the way galaxies rotate, affects the way galaxies form, it affects the way the universe moves as a whole because of all this matter, but we don't know what that is. And then 68.5% of the composition of our universe is this dark energy. There's something contributing to the expansion of our universe and making it expand faster. In terms of evidence for dark matter, there's a lot of it. There's galaxy rotation curves, which I'll talk about more on the next slide. There's galaxy clusters. If you look at the way galaxies orbit each other, basically, you can show that there's dark matter. There's matter that we can't see that is influencing the way these clusters orbit each other. There's colliding galaxies, which is really interesting. You can look at things like this image. This image is the Bullet cluster, and so this is two galaxies which collided, and their areas, and we can image this Bullet cluster both with visible light and with radio waves and microwaves and many different spectra, and we can also use different techniques to measure the mass density of this galaxy cluster where these two galaxies collided. And pictured in the red here is kind of where the visible material is. Right? So this is the gas and things like that. But pictured in blue in this image and pictured kind of just in the contour lines, the green images here is where all the mass is. Right? So as these two galaxies collided, and all the stars in this picture are in the background pretty much, but as these two galaxies collided, all the gas interacted with itself and kind of slowed down a bit, and that ended up all in this region. But the dark matter, which doesn't really interact very much from one galaxy, just passed through the dark matter from the other galaxy, and that's where all the matter is. Okay, so the majority of the matter is not where the visible matter is in these colliding galaxies. And there's other examples of this besides the Bullet cluster that are actively being studied now. And the cosmic microwave background is also great evidence for dark matter. You can study the structure in the cosmic microwave background, and that gives more evidence for dark matter. And then the large-scale structure of the universe, what I talked about earlier, that on huge, huge scales, much, much bigger than a galaxy. If you look at kind of the relative density of matter in our universe, you get these strings. You get these dense regions where there are areas with very, very few galaxies, and then there's areas where there's more galactic structure, and this is something you could predict. If you include dark matter in your model and you simulate the universe as a whole, you get these gravity causing everything to form structures like this. So lots of really cool stuff going on with this type of research right now. In terms of galactic rotation curves, if you just looked at a galaxy and plotted from 0 being the center of the galaxy and the x-axis here just being distance from the center of the galaxy, so again, 10,000 light years, 20,000 light years, 30,000 light years, And if you measure the velocity of objects as they rotate around this galaxy, in this direction, um, you would predict, just with the visible matter, you'd predict rotation curves like this, meaning the material at greater distances would be moving at slower speed, way far away from the center of the galaxy. What we actually measure is this curve here, right? That the velocity seems to be increasing the further you get out from the center of the galaxy. And the only way to really explain that is if there's a giant halo of dark matter. Maybe it's some particle that is really heavy and stable and doesn't, barely interacts at all, but it does interact gravitationally, and that, something like that. So some big halo of dark matter is somehow influencing the galactic rotation curves. We can also study supernova. Supernova can be used as standard candles. Certain types of supernova always blow up and emit basically the same amount of energy, and they should all be the same brightness. And using that fact, you can actually estimate the distance a supernova is away from you. And in 2011, this supernova cosmology project, which was studying a lot of these supernova, had discovered that indeed not only are these really far away objects, these supernova, moving away from us like everything else in the universe, but the universe is actually expanding more rapidly recently, right? And so that's another big interesting thing that's currently being studied, and something that could be evidence of this dark energy idea. Other things and more evidence for dark matter, and also just a real cool thing that we can use to study the universe, is the concept of gravitational lensing. Light from a distant source can bend around a massive object. Okay, so if we have, things like stars and galaxies really far away, some source really far away from Earth, and in between that star and us, there's some galactic cluster or some really massive object, space actually bends and light bends around that massive object. And so you can see the light from here, the light that originates here, we actually observe it coming from over here because it kind of bends around this heavy object. Right? So you can actually see light twice from the same object in some cases. Right? We can be here, a source of light here, the light could bend around the object in this direction and we could see it, and the light could bend around the object in this direction and we could see it. So this is called strong lensing, and it leads to these beautiful things like an Einstein cross, where the same object is visible 4 times here, or an Einstein ring, where all the light from a galaxy or something like that is kind of being spread out around this ring. Right? So that's a really beautiful thing to see. That's the concept of strong lensing. There's also a very actively studied tool called weak lensing, which is much smaller distortions, but using data analysis, you can still measure all these distortions through statistical techniques to understand the universe in more ways. So that's an area of active study. And there's also microlensing. This is something where there's no visible distortion, but some very small change in brightness as time moves on. And so with strong lensing, weak lensing, and microlensing, cosmologists are actively studying a lot of the behavior of the universe and trying to understand dark matter and dark energy and things like that. And telescopes like that, LSST, the Vera Rubin telescope, will do a lot of this type of measurements. Okay, and I'll kind of end here with just some more beautiful pictures. Here's a Hubble image where we have a lot of really distant galaxies, and we have an Einstein cross. Just a beautiful thing to image. And here's a whole bunch of Einstein rings from the Sloan Digital Sky Survey. And so, yeah, cosmology is really neat, and please let me know if you have any questions on it.